Swayam Prabha. Digital India. Educated India.
Go back to the process of matrices and also the transformation. So if I remember, I wrote x, y as cos theta, sin theta, minus sin theta, cos theta, x prime, y prime. Okay. Basically, what this is if you have to write it carefully, these are all unit vectors. Okay. This element is x dotted x prime. This element. Okay. This element is x dotted y prime. That's what that is. So you can see how simple transformation properties come out, and this is y dotted with x prime. And this is y dotted with y prime. And that's x prime, y prime. Okay? That's what that is. Okay, if you look at the picture. Okay. You see that? So x is x with x prime length multiplied by x prime plus y prime multiplied by y prime. That length. Okay. Y is y with x prime length multiplied by x prime and y prime length, this one, multiplied by y prime. So this is the standard. Now in 3 dimensions, if you have to do that, suppose you have 3-dimensional vectors, and suppose you have a vector. And for simplicity, we will rotate the vector about, say, this is x, this is y, this is z. Okay? We'll rotate the vector about the z-axis. Okay? So that when you rotate the vector, it will go like this, go around that. Okay? So you want to take a small rotation, this point. Same vector, when it is rotated, it comes by an angle theta. Okay? You can either do that, or you can rotate the coordinates, the x coordinates. You rotate xn to x prime, and rotate y to y prime. Okay? In the plane, z is perpendicular. So you have x here, y here, something like that. You rotate x and y about z. That's the simplest rotation. 3-dimensional rotations, general rotations require 3 angles. But the simplest of them is 1-angle rotation when it is about 1 axis. Okay? So if you do the z-axis rotation, the same thing, x prime, y prime. So let me follow the convention, call this as y prime, z prime. And this rotated axis as x prime, y prime. Z and z prime are the same because you are rotating about the z-axis, nothing moves there. So if you do this, you will see that this is connected to x, y, and z, x, y prime, x prime, y prime, and z prime by cos theta, sin theta, 0 minus sin theta, cos theta, 0, 0, 0, 1. Okay? You can see right away the block. Because x prime and y prime will only change among themselves, x and y. It won't involve z. Therefore, you see x and y, when the new coordinate, will involve only these 2. And now you remember the matrix multiplication. This multiplied by that, this multiplied by that, this multiplied by that. So it's cos theta sin. So what is this? This is 3 by 3 This is what? 3 by 1. So what should you get? 3 by 1. Okay, you get that. Okay. So you see that the matrix multiplication tells you that, again, it is a simple one. The more difficult one, or the more general one, is known as Euler rotation, general Euler rotation. The famous mathematician. Okay. That involves all the three angles. To see that, I will bring in an animation some other time, in some other class. Today is very difficult to see. The reason for introducing this is to define vectors formally. Okay? Now, you see that the coordinates x prime, y prime, z prime are rotated to x, y, z. From here, they are rotated x, y, z by this transformation matrix. Now, here is a vector A. So, the vector A has coordinates A x prime, A y prime, A y prime, and A z prime. Okay. Now, what happens to them and what is the relationship between AX, AY, and AZ, the new components, with the old components, x prime, y prime, z prime? What is that relationship? It's exactly the same relationship. If there are three quantities which transform when the coordinates are rotated by the same transformation rule, those three quantities form a vector. That's a definition in 3 dimension. Okay? If there are three quantities, which when a coordinate system is transferred in 3 dimension by a transformation matrix like that to the new coordinate system, if those three quantities are connected to the corresponding three new quantities by the same matrix cos theta, sin theta, then the quantities A, x, a, y, a, z form a vector. Is exactly the same matrix, not the opposite, not the inverse. I know where you are getting to. The three quantities should be, see, you either rotate the coordinate system, but if you rotate the system in the opposite direction, the angle will change. Okay? Therefore, the definition of a vector is, in 3 dimension, is a set of three quantities which form the same transformation rule to the new three quantities as was the rule obeyed by the coordinate system themselves. Okay? This defines a vector. Now, if it is a 3-angle formula, full-fledged 3-dimensional rotation, it's the same rule. Okay? Except that the transformation matrix is a much more complex matrix. Okay? What about a scalar? Yes?
So why can't we apply this for 2-dimensional?
You can do the same thing for 2 dimensions. Yeah, it's the same.
So for R plus N?
2-dimensional vector, there are only two quantities, AX and AY, AX prime and AY prime. Therefore, the transformation rule for the 2 dimension, why I'm doing it for 3 dimension is, it's easier for me to explain the tensor properties. Of course, you can do the same thing for 2 dimensions. There are two quantities, and there are two quantities. There are two coordinates, there are two new coordinates. The relationship between the two should be the same relationship between the two new transformed components. That's all. That's all it is. Yeah. Okay. What is a scalar? No transformation. The scalar here is ax square plus ay square plus az square. If you want square root, the magnitude. And the new quantity is ax, sorry, this is prime, prime, prime. And the new quantity is ax square plus ay square plus az square. They are both equal. There is no transformation. Okay. Now, what is a tensor? To do that, I still have to introduce one more thing. We saw one multiplication property, right? A, B, C, D. P, Q, R, S. So you have done the matrix multiplication. That is another matrix multiplication known as a direct product representation multiplication. Not standard multiplication, direct multiplication, direct product. So the direct product is written with a multiplication sign circled by them. Okay? The direct product is defined for any two matrices as follows. A, now the direct product is, this is a 2 by 2, this is a 2 by 2. The direct product is 2 by 2 and 2 by 2, so it's a 4 by 4. Okay, product of the rows, product of the columns. Now, what is the element here? A, all four of them, AP, AQ, AR, AS. Okay, A multiplied by the entire matrix. Next is B multiplied by the entire matrix, BP, BQ, BR, BS. Okay. C multiplied by the entire matrix, CP, CQ, CR, CS, and then BP, BQ, DR, DS. This is called the direct product of two matrices. Or tensor product, usually we don't use the word tensor, but tensor product of two matrices. See, this is different from the simple multiplication. The simple multiplication will give you AP plus BQ, BR. Then you have AQ plus BS, CR plus CP plus DR, and then you have CQ plus DS. This is still a 2 by 2. Almost like the scale, like the vector, the dot product kind of a knowledge, basic idea. So that's a simple product. This one is a direct product. Okay? Yes?
In which cases do we apply?
Sorry? In?
Real life, which cases do we apply?
In real life, all of quantum mechanics. Okay, all of physics if you want to. See, the definition of tensor is going to depend on this. The definition of tensor quantity is that the moment in 3 dimension you talk about 3 vectors, 3 basis vectors, x, y, z. Now I will tell you what that is, okay? So, the moment you go to a second rank tensor, I said there is a vector A, AX, X, AY, Y, AY, Z. Okay. So now this goes to AX prime. Sorry, this is X prime, Y prime, Y prime. That's what we started as the initial one. And then it goes to AX, X, AY, Y, AZ, Z. Okay. Now, a tensor AA now consists of 9 of these, namely AX prime square, X prime, plus AX prime, AY prime, X prime, Y prime, plus AX prime, AZ prime, X prime, Z prime. You can write all the 9, and the last one is A, Z prime, A, Z prime, Z prime, Z prime. There are 9 of these, okay? And here, there are 9 of these. After coordinate rotation, these components are different from these components. What is the relationship? Now, the quantities x prime, suppose we write this x, y, z is equal to R, a matrix, x prime, y prime, z prime. R is a 3 by 3 matrix. We saw that, cos theta, sin theta, minus sin theta, cos theta, that matrix. Now, if you write x, y, z, yx, yy, yz, zx, zy, zz, okay? And if you want to connect this with the original one, x prime, x prime, x prime, y prime, x prime, z prime before rotation, y prime, x prime, y prime, y prime, y prime, z prime, z prime, x prime, z prime, y prime, z prime, z prime. What is the matrix which connects these quantities under rotation of the coordinate system to these quantities? This is the direct product of R3 by 3 with itself. Okay? Yeah. No, louder. Yeah. Tell me. No, XX is a dyad. Anything that depends on two directions. The pair of directions may be the same. X and Y, the pair of directions is X and Y, two directions. So a tensor has quantities which are defined by two directions. 9 of them. Either AX prime, AY prime, or AX prime, AZ prime, whatever it is. Each one component requires specification of two coordinate directions. In a vector, each component requires a specification of one direction. In a second rank tensor, it requires a specification of two directions. In a third rank tensor, it's going to require the direction of three directions, XXX, XXY, all those things. Okay? So second rank tensor is a generalization of the properties of the system under transformation of coordinates. See, coordinates are only three. Okay? Coordinates are only x, y, z because we are in 3 dimensions. Therefore, a second rank tensor involves 9 pairs of directions. Except that x prime is still only one direction. But the quantity may depend on x prime, what happens in x prime and what happens in x prime. Okay? But you have the other. There are 8 of them. So there is a total of 9 of these pairs. Each one is called a dyad. X prime is called one of the 9 dyads. Okay? Like basis vector that you say in vectors, you say they are unit vectors. Here you say unit dyad. Yeah. Except that there are 9 of them. What happens to these 9 under coordinate rotation of R of these coordinates x, y, y prime, z prime to these 9 transform like the product of R3, R cross, R cross. What is the product of R cross, R cross? You have already seen that. It's cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, 1. Now, you want to take the direct product of this with cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, 1. You are going to get 9 by 9 matrix. Right? That matrix is the transformation matrix of these dyads to the new coordinate system. Therefore, a quantity is a tensor if it has 9 components, 9 components, all of which transform under coordinate rotation to the new 9 components by the same rule. Okay, so what is that rule? You write AX prime XX, AXY, yeah, AXZ. You write all the way down to AZZ. So this should be the same transformation or cross R, okay? AX prime, X prime, AX prime, Y prime, AZ prime, Z prime. So it is the transformation property which under coordinate rotation, which is the general way of writing. Yes, yeah, writing the tensors. Come again? No. I put the prime as the first one in the previous lecture. Yeah. X prime, Y prime dyad and Y prime, X prime. How do they differ? Well, find out. I'll give you the answer. Find out. What is the difference? They are basically unit dyads. The dyad X prime, Y prime, again, I mean, I can only explain in terms of mathematics. When you say AA dotted with B, now this is a dyad, this is a 9 quantity, this is a vector, okay? So you have X, Y, Z. Now, if you have X prime, Y prime dotted with X versus Y prime, X prime dotted with X, now you see this will be 0. Y prime, X prime. And what is left over is X prime. So if you do a scalar product of a tensor with another vector, you get a vector. If you take a scalar product of a vector with vector, you get a number. Ax square plus ay square plus az square, number. If you do a tensor product, a scalar product of a tensor, so the answer is, what is the difference between X prime, Y prime and Y prime, X prime? Depends on what you are operating on. Suppose, instead of this, suppose you do this, B dot AA, you have a problem. This will work only with the Y. This will work only with the X. So the product that you take will have different components. So each one is a unique two directions. The non-commutability is very important. X prime, Y prime is not the same as Y prime, X prime. Okay? With respect to multiplication properties, with respect to the tensor properties defined further, these things are fundamentally independent quantities. No, right now I'm not. There is no cross product we can define. Yeah, what we can define is one more product. We can define, we call this as two products. So what will happen is you do this first, what is left over is AB, and then you do one more dot product. Okay, I'll give you a problem sheet. Why don't you work those things out? Just about 3 or 4 problems to see how to follow the algebra. Okay, those are details of the algebra. Okay, so but what is important for you to understand is that mathematical quantities, why these are necessary mathematics of for a chemist to talk about all these things. Okay, a scalar, a second rank tensor, or a vector, and so on. Everything that we deal with in physical quantity belongs to one of these. Okay? If you talk about dipole moment, it's a vector. If you talk about the polarizability of a molecule in an electric field, see, the molecules are charged, A and B. You know, if they are not the same atoms, they are polarized. If there is a positive charge on one side and a negative charge, obviously the positive side of the molecule will be repelled by the positive charge. The negative side will be pulled by. Therefore, the molecule can polarize itself. You put a molecule in a plate between 2 plates, one with the positive and one with the negative. You put a molecule A, B. A is slightly more electronegative, B is electropositive. What will be the orientation? The molecule will orient towards the positive charge, so the molecule is polarized. In that process, the bonds may slightly be pulled out. The negative charge may pull the electron towards it. Okay, the positive charge pull the positive charge towards it. The positive side may pull the electron towards it. So the bond may be polarized, slightly extended. This polarization property is a tensorial property, and you study this using Raman spectroscopy. Dipole moment is important for all spectroscopy, microwave, infrared spectroscopy, electronic spectroscopy, and so on. And then when you go to magnetic resonance, there is a phenomenon called the chemical shift and chemical shielding. And these properties are all, it was found out, mathematically, they belong to tensorial characters. Therefore, when you measure, it is not just one measurement that you will take, it's not one property you will measure, you may measure multiple components. And so the process of what you call studying these molecules in detail using experiments which are very highly developed these days than they were, say, 50 years ago. All of these things give credence to the idea, the mathematical idea, that the fundamental properties of molecular systems have very clear observations, like either they are vectorial quantities or they are tensorial quantities or they are scalars and so on. Energy, for example, of the molecule is always a scalar, doesn't have a direction. Energy is a number. Angular momentum of the molecule is a vector. Polarizability and susceptibility, magnetic susceptibility, if you think about it, they can be tensorial. Moment of inertia. For microwave spectroscopy, one needs to know the moment of inertia of the molecule. The moment of inertia looks like a very simple definition. mr square for a diatomic molecule. You can say that from the center. That's because you only one R. But if you have many, if the molecule has a structure and the axis, the atoms are in different locations and they have different distances, someday I will talk to you about what is the moment of inertia tensor, and I'll tell you what it is. Yeah. So you will see these properties are important. So even before you study quantum mechanics, even before you explain these properties using experimental quantum mechanics, you see that you have to have a fundamental understanding of these. And there's no escaping the mathematics and physics of the basic descriptions that you have. Okay? So the idea here is this one, the transformation. And therefore, now you can say what a third rank tensor is. A third rank tensor will not have 9. How many it will have? 27, because one x is to be added to all of them, one y is to be added to all of them, and one z is to be added to all of them. So you have 27 of them. So 27 quantities. So what is the transformation of a third rank tensor? R cross R cross R. One more. Okay. And therefore, an nth rank tensor contains 3 raised to n quantities. This is 3 square, 3 cube, 3 raised to n quantities, which undergo transformation by the rotational matrix property n times, okay? And it has 3 raised to n experimentally measurable or assignable quantities, which will undergo transformation by exactly the same relation. Then that is called an nth rank tensor. Such a quantity is called an nth rank tensor. Now, the definition of tensor, the definition of, there is one more definition involving derivatives, but you have not been introduced to derivatives, right? It's coming only in the next semester. This year, calculus. So you know the simple derivatives d by dx is all done, okay? So maybe in the next class I'll tell you what is the corresponding definition using derivatives for tensors. They are the same, not very, very different, but they're all equivalent ways of doing things. Okay? I wanted to do something else in these 2 classes. I thought I would take the quantum state and write down the matrices and go to the properties and so on. But then I found out in your book, thanks, I mean, I was happy to look at your book about half an hour before the lecture. In the 11th standard, there is no mention of linear algebra. There is no mention of vectors. And there is obviously no mention of matrices. And then the 12th standard book has in part B, not even in part A, I think, part B. So now you got a slight introduction to matrices, and any free class I get, I'll continue on matrices and tell you more than what your textbook tells you. Okay? That is important for you to understand why the present day, the mechanics that we have, the understanding that we have of molecular systems using computational methods. Okay? Almost all of them today use matrices and numerical methods. It's diagonalization of matrices, and it's associating matrices with the properties that we want to study and measure, and then finding out what are called the eigenvalues associated with the matrices, and then using these eigenvalues to understand the transformation that happens when you excite the molecule. So the whole of chemistry has been completely transformed with the arrival of quantum mechanics to study molecular properties in the computer long before we can actually do experiments. And today we can replicate the molecular property studies in the computer with a lot less money than doing those experiments in the laboratory with hundreds of chemists paid a salary of, 100,000 rupees or whatever it is. Today, the average salary for a scientist in a company should be at least more than 50, 70,000 rupees to start with per month. And you have to engage 100 chemists to study one drug in detail over 3 years or 4 years. A lot of this can be done with a little bit of hindsight from quantum mechanics on the desktop computer and on slightly more extended computing systems with the cloud and so on. And once you have a reasonable conclusion, then you tell the laboratory, these are the experiments which are relevant and which will give you probably the results. So the number of experiments in designing a drug gets reduced the moment you apply quantum mechanics sensibly. And the entire process is computational. You can't do it by hand. You have to use basically programs, and there are programs which contain 2.5 million lines and so on. You just get it as a binary. You don't even see what the code is. And there are front-end windows saying, do this, do this, do this, do this, and then you get the answer. You don't even know what that individually does. Of course, the theoretical chemists will know, but not the others. So today, it is important to see that basic things that you pick up in these lectures hopefully will help you to quickly build your own learning process. Okay, thanks.